Hello, hello, hello. Okay. So, welcome everyone to webinar number 10. The topic is reflection and refraction. So basically we're talking about light. Okay, and without any further ado, I'll get going with some problems. So I have two easy questions, some quite hard. So hopefully there's a little bit for everyone today. First, I just wanted to talk about waves a little bit. So, as you know, light is a wave. How do we know that light is a wave? Because it behaves like a wave. Later on, you will learn that light is also a particle, but that's another story. Anyways, that light is made out of particles called uh, called sorry, photons, of course. Okay, so let's look at waves first. This is a rope, and if you ever were given a long rope, I'm sure that you're just like me. The first thing you've done is something like this. And you send a wave along a long rope. Okay, that is if the rope is infinite. However, if the rope is not infinite and is tied to an end at the other end, we flick it and then it reflects. Okay? Waves reflect when they encounter, well, what we call an interface. An interface, it could be an interface between two media, sorry. It could be a wall, could be a fixed point. Yes, but waves reflect. And they can have two different reflections. So look what happens when it reflects. It reflects downwards. That means it changes phase. The phase changes upon reflection. Whereas if I introduce a loose end, that means an end that is not tied to anything, look what happens. It reflects but without a phase change. So this is quite an interesting thing. We won't be covering phase in this section, but this is something to look forward to when you go into year 12. So cool. So waves reflect. Now, imagine if the rope wasn't uniform, but it had two different two different media. So you would see something like this. So imagine there's a thin rope, half of the rope is thin, and then the other half of the rope is thick. You would see something like this. It goes fast, 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 and then goes faster, or it goes fast, 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 and then suddenly slows down. So waves travel differently in different media. So this is what we call refraction. So you can show a refraction rope. Unfortunately, I don't have two ropes. If I had two ropes, that's what I would do. I would take a thin rope and a thick rope, and I would fling it, and you would see that the wave goes at different speeds along the thin rope and the thick rope. So this is refraction. So on the boundary, on the interface between two ropes, the wave changes speed. Nice. Let's look at other waves. So this is a water wave. So this is a source of waves. So these are ripples on a pond. So let's say something on the surface of the water goes up and down, produces waves. And we can see, well, we can take an obstacle. Now, if I take an obstacle, you see that the waves reflect of that obstacle. So you can see waves coming in and they're reflecting to the right. So clear the waves. Let's see if I can get a better picture. So start the waves. So you can definitely see that the waves are being reflected in this direction. So I'm showing with my finger, obviously. That's a bit silly. But yeah, waves go like this. You can clearly see that the waves are traveling to the right as well as going down. Okay. What else can I show you? A mirror. Certainly. Do I have a plane mirror? Refraction. Okay, I don't have. Okay, let's see if I can do. What's a Lloyd's mirror? Oh, that's an interesting pattern. Okay, anyways, waves reflect. Waves reflect. Look, this is a ray of light, and a ray of light. So waves can be represented as wave fronts. We call them wave fronts, or they can be represented as rays. So the ray just shows the direction of the wave. So a ray doesn't really exist. It's not a physical thing. It just shows the direction of the wave. Incidentally, when you talk about laser rays, you can actually see it. Although you don't see the actual ray, you see light reflected of tiny bits of debris which are in the air all the time. So when you see a laser beam, you don't actually see the laser beam. You see the laser beam being reflected of tiny particles. Anyways, you have a reflection, of course, and you have a refraction. You normally have a reflection and a refraction. Sometimes you don't have refraction, and sometimes you don't have reflection. The only way not to have reflection is to not have an interface. So let's go, we are going from air to water. Some of the light goes through, some of the light is reflected. But if both of them were water, you would see that there's no reflection, only. I can't really call it refraction, it just passes through. Okay, light passes through. And if this material is air, let's see how this looks like in terms of waves. Well, of course, sort of like this, but let's see if we can get a more realistic picture. Clear waves, example, refraction. So you can see waves are coming from the right. So waves are traveling from the right. And they will be hitting the boundary. This is the picture that I wanted to get. Okay, so you can see that the light, or the wave, travels like this. and then some of it is reflected, and some of it is refracted. Okay, so hopefully that makes sense. Reflection and refraction. And we need to talk about total internal reflection a little bit. Well, okay. Reflection area, sorry, I'll talk a little bit more here. So if we draw a normal line, so this line is normal to the interface between the two medium, and this angle, let's call it angle of theta 1, and let's call this theta 2. Let's call this theta 2. This is theta 1, and we call this theta 3. So theta 1 is the angle of incidence. Angle of incidence. Theta 2 is the angle of refraction. And theta 3, angle of reflection. Okay, the law of reflection says that theta 1, so law of reflection, it says that theta 1 is always equal to theta 3. That's the law of reflection. And law of refraction says that if the refractive index of this material is N1, the refractive material of this material is N2, then we have the Snell's law of refraction, which is N1 multiplied by sine theta 1 equals N2 multiplied by sine theta 2. That is Snell's law of refraction. Sometimes it's written simpler, like this. N is sine of the angle of incidence divided by sine of the angle of refraction. This is not a very good formula because it's not always true, because sometimes if you are going from water to air, for example, it's sine R over sine I. So it's the other way around. Okay, but anyways, so this is Snell's law of reflection. Okay, so hopefully that makes sense. You should know this, so this shouldn't be new to you. Total internal reflection occurs when you're traveling from water to air, for example, from a denser material to a less dense material, air. And if you start increasing the angle of incidence, so the angle of incidence is 0, 10, 20, 30, 40. At about 40 something-ish degrees, 46, 47, 48, the refracted ray disappears. Look, refracted ray disappears and you only have reflection. So this angle is known as the critical angle. Okay. At some angle of incidence, if traveling from denser to less dense medium, the refracted ray disappears. Refracted ray disappears. This angle is known as the critical. So this happens when the angle of incidence is equal to the critical angle. Critical angle. So if this is N1 and N2, we can say that the angle of refraction, so let's say this is θ1, this is θ2. So this happens when θ2 is 90 degrees. So we write down Snell's law. So N1 sine θ1 equals N2 sine θ2. So if θ2 is 90, so that's N1 multiplied by sine critical equals N2 multiplied by sine 90. If then I equals critical. And the sine of the critical angle is N2 divided by N1. Right? If N2 is air, N2 is air, and air is 1, then sine C is equal to 1 over N. Okay. Good. So where N1 is the denser material. Well, you don't really need to memorize that, which one is which, because, well, sine is used. Well, we will do Fermat's principle at the end. There is an explanation, but it's a little bit beyond. It can be explained using the Fermat's principle, or it can be explained using Fresnel's principle. So neither of them. So I will cover Fermat's principle at the end of this session, and I don't think I can cover Huygens Fresnel's wavelets principle. Certainly, I can't show you the Snell's law today, like the derivation of Snell's law. So apologies for that. Anyways, so the critical angle. So the critical angle is an angle at which the refraction no longer takes place. So bam. So for water, it's about 49 degrees. Let's check if that is true. So critical angle for water is approximately 49 degrees. That's measured. Now we know that the refractive index of water is 1.33. So the critical angle should be inverse sine of 1 over 1.33, which is inverse sine of 1.33, inverse sine of 1 over 1.33, thank you, 48.8 degrees, 48.8 degrees, so true. Now let's try for glass. The critical angle for glass Let's make a prediction. So glass is 1.5. So the critical angle for glass should be the inverse sine of 1 over 1.5. And inverse sine 1.5, it should be 41.8 degrees. So my prediction that if I use glass, my refraction would disappear at 42 degrees. So 10, 20, 30, 40, 43. Okay, so really close. Okay, nice. Now coming back. Now I like this question, and this is a very typical university interview question. What percentage of the Earth's surface is visible to astronauts on the ISS? Okay. So how does that work? Well, light travels in straight lines, as you know. So if you are if this is the okay. I won't embarrass myself. I will use a circle. So this is planet Earth. Now, the ISS is somewhere above the planet Earth, and the most what you can see is if you draw a tangent line like this and another tangent line like this. This is the visible part of the planet. So I'll use what, green. This is the visible part. Now, it's obviously going to be like some sort of circle. So the visible part of the planet. And the rest is invisible because it's behind the horizon. Okay, so what do we need? Well, we need the radius of the Earth, and a quick Googling of that, or quick remembering, is 6,400 kilometers. And quick Googling of the height of the ISS will tell you that this is 400 kilometers. Okay, so not that much if you think about it. Okay, so I'll probably draw a line to the middle. So that's 6,400. And this is the radius of the Earth. Radius of the Earth. This is r plus h. And well, what do we want? Well, we probably want this. We want to find this angle, theta, because that would give us what would that give us? Section. We want to find this angle. Okay, so you can find cos theta, cos of that angle, because this is a right angle triangle, is the r divided by r plus h. Okay, where h is the height above the Earth for the, so r is 6,400 kilometers, and h is 400 kilometers. Now, four pi r squared. We need the formula for a sector of a sphere. Ooh, I don't remember those. I didn't remember that. I have to look it up. Sector of a sphere. Spherical sector. Okay. Spherical is called a spherical cone. Volume. Two-thirds. Spherical. Volume of spherical cone. So apologies. Volume and spherical cone. Oh, we don't need the volume, we need the area. Oh, okay. That makes sense. Okay. We don't need the volume. We can take the area. Yeah, I don't remember all the formulas. So you want the area of this section of the sphere, and the area is given by this formula. Area is pi r multiplied by 2h plus a. Now we need to be careful what h is, because h is not the same h plus a. A is the radius. Okay, so let's introduce some variables. So we want to find this. This is a, and this is h. H is the height. Well, let's call this, let's call it h dash. Okay, so the visible area, well, let's calculate a first. So a, because this angle is theta, so from using trigonometry, so this is r sine theta. And to find h1 is, well, it's r minus r cos theta. Because if you look at it, this line is r, this one, and then this is r cos theta. Sorry for being messy, but this line is r, this is theta, this is r cos theta. So h dash is r minus r cos theta. I hope that makes sense. I'll rub this out just to make it less horrible. Okay, so we found those. Now we can substitute. So visible area is A visible equals pi r multiplied by 2h, 2h dash, so 2r minus 2r cos theta plus A plus r sine theta. And we can find cos theta is that. So we can work out sine theta using the trig identity. Sine theta is square root of 1 minus r squared over r squared plus r plus h squared. So that's going to be r plus h. R squared minus is going to be h squared minus 2rh, like this. And we sub that in. Visible is, well, I don't think we can actually calculate that, because this is 64 divided by 68. There's 64 divided by 68. So we can simplify this 16/17, and this is square root, so 117 squared minus 16 squared, 33 root 33/17. Okay, the visible is pi r squared multiplied by 2 minus 2 cos theta plus sine theta, which is pi r squared multiplied by 2 minus 2 times 16/17 minus root 33/17 square bracket. So, I don't need brackets. So that is that is 0.455 pi r squared. Okay, 456 pi r squared. And the area of the Earth is 4 pi r squared, of course. So the percentage visible is 0.456 pi r squared over 4 pi r squared, which is divided by 4, which is 11.4%, approximately 11.4%. It's quite interesting. You would think you would see half the Earth from the International Space Station, but no, you only see 11.4% of the planet at a time. The reason for that is that you're not very high above the ground. It's only 400 kilometers. So yes, I repeat, this is a very typical question from a university interview. So I would, if you didn't fully understand how I did it, I would try to do it by yourself and get there. Okay, now back to Earth. Problem 4. This is a construction problem. So this is a very unusual problem. You wouldn't encounter anything like that on your A-level course or equivalent, whatever course you're doing. I think most of you are doing, most of you will be doing A level. So construct the ray if the ratio of refractive indices is equal to the ratio of the radii. Okay, so we have two half spheres. And we have the refractive index of the first one is N1. The refractive index on the second one is N2. The radius of the big one, of the small ones, is R1 radius, and this radius of the second one is R2. So you want to construct. So what does it mean to construct? Construct, you're not allowed to measure stuff. You're not allowed to do any calculations. So the only thing you can do is, well, use a straight edge and a pencil. Okay, so let's start constructing. So I will draw. Well, first of all, I will write down Snell's law of refraction. So I would say that I would label the angle of a θ1, angle of incidence, and I would write that N1 sine θ2 must equal to N2, N1 sine θ1 sine θ2. Okay. Now, not sure how this helps. It says the refractive index, the ratio of the refractive indices, so N1 to N2 is equal to R1 to R2. So somehow we need to link the radius of the sphere. And we do it in the following way. Well, if I take this as my first half sphere, and I draw a radius, R1, this angle is θ1. And let me just draw another one, like another line here. And let me call that x1. x1 is the distance from this line to point B. Point B is where the ray enters the glass. And I can write that sine θ1, sine of this angle, is equal to the opposite, x1, divided by hypotenuse, which is r1. That might come in useful. Okay. Now, when the ray goes through, it refracts. So the refractive index of this is greater, so it goes like this way. And I've got θ2, and I also get x2. So x2 is where, like this, so similar fashion. This is r2. So sine θ2 is x2 over r2. Well, this probably is useful as well. Okay, so let's try to combine these four equations together and get something meaningful out of it. Well, let's start with the Snell's law. So we'll write the Snell's law, and from here I will write that N1 is R1 over R2 times N2. So I'll sub that in. So that's N R1 over R2 multiplied by N2. Multiplied by sine θ1. Sine θ1 is x1 over R1 equals N2 multiplied by sine θ2, which is x2 over R2. So I'm kind of combining all of these into one. Now I can start simplifying. I can see that N2 cancels, R1 cancels, R2 cancels. Oh, beautiful. I have x1 equals to x2. And that's a very important deal. So the x1, this distance, and this distance is going to be the same. And that is how I can make my construction. So that means that this line, if I continue this line down, so using a straight edge, this is x1. Now, if I draw a parallel line, and here, this is going to be x2, and this line is going to be the continuation of that ray. So the light goes in through here and then refracts like this. So all I did is just continued this line here. I realized, so I've made some calculations and I saw that I did some algebra and I saw that x1 has to equal to x2, and this is how I can make my construction. So quite an interesting one. N is the refractive index of glass. N is refractive index. Does who if you know what refractive index is, type 1 please. If you don't know what refractive index is, type 0 please. Okay, I should have started with this. Okay. When light travels into glass, so let's go up here and talk about the refractive index. Refractive index. When light enters, well, speed of light is different in different materials. Let's put it this way. Speed of light is different in different materials. The fastest light can travel is in vacuum. Light is fastest in a vacuum. The refractive index is the speed of light in vacuum divided by the speed of light in that material. So the refractive index of water is 1.33, means light is 1.33 times slower in water compared to vacuum. And the same for the N for glass is 1.5, means light is 1.5 times slower. The diamond is 2.4. So it's 2.5 times slower in diamond compared to compared to vacuum. The refractive index of air is 1, or approximately 1. That means it travels in air just as fast as it travels in a vacuum. Okay. Does everyone understand what the refractive index is now? 1 or 0? Okay. It turns out that if you send light traveling from one material to another, so let's say from air to glass, if you send light from air to glass, so this is θ1, this is θ2. N1 is the refractive index of air, in this particular case is 1, and this is the refractive index of water, N2, and this is 1.5. And the Snell's law of refraction says that the sine of θ1 multiplied by N1 must equal to N2 multiplied by sine θ2. That's Snell's law of refraction. And so sine θ1 divided by sine θ2 must equal to N2 over N1. In this particular case, this is 1.5 divided by 1, and this must equal to sine. Now, let's measure the angle. The angle of incidence is 44 sine 44 divided by sine, or approximately, of course. I'm unlikely to get 26 sine 26 should be 1.5. And if you do the calculation, so sine 44 divided by sine 22, if I do, 26, and it's 1.58. Okay, so it's approximately 1.5. Well, it's not. It's approximately 1.6, but I must have messed up the measurement of the angle. Okay. This is Snell's law. Now, when, as I was showing before, if you go from a denser material, so if you go from glass to air, for example, at some point, your refracted ray disappears, and that's called total internal reflection. Total internal reflection. Okay. Good. All right, so I hope that makes sense. Problem 5. A parallel beam of light falls on a glass semisphere of radius 2 centimeters, refractive index of n equals 1.41. Find the radius of the bright spot on the screen, which is placed to 4.82 centimeters from the center of the sphere. What on earth are they talking about? Well, let's do this experiment. So we have a glass prism, which is placed like that, and a beam of light. And as you can see, that the light doesn't go straight, it refracts upwards. If you shine light from the bottom, it just stops being refracted. It just reflects from the surface. The total internal reflection occurs at the top. So it refracts, but at some point, just light stops going through the glass prism. So light just doesn't go through. So it goes through, and bam, bam. No light goes through. So the size of the bright spot is determined by the refractive index. Okay. So first of all, we need to work out the maximum angle. Okay. So this ray, so the idea is that this ray would bounce through but refract. This ray will go through but refract. This ray will go through and refract. This ray will go through and refract. This ray will reflect into the glass, so it won't leave. So you would see a bright spot here. And you need to find the radius of that spot. Okay, so I'll make a picture of that because we'll need this is the general idea. Okay. So at some point, in the critical position, you would see a light ray going straight through and then being refracted along the boundary. So this would, if you draw a normal line, this angle, theta 1, is going to be the critical angle for glass because the refracted ray is theta 2, which is 90 degrees. So that's the furthest away from the center that you can still be refracted. So that this is the point where refraction stops. So, and this is the radius, R, and this is, well, let's call it H. Okay. And theta 1 is the critical angle. So theta 1 is, so sine theta, so N1, well, we already know that sine theta 1, so that's the critical angle, is 1 over n of the refractive index. So theta 1 is inverse sine of 1 over n, which is the inverse sine of 1 over 1.41. Ooh, interestingly enough, that's 45 degrees. So that's approximately 45 degrees. Okay, that's nice. The fact that it is 45 kind of makes life easier for us. Now, we want to find h. H is r multiplied by sine theta 1. So that's going to be, that's 2 divided by root 2, which is root 2. Okay, h is root 2 centimeters, so it's approximately 1.41 centimeters. Okay. Now, we need to find this radius. So we need to find the radius of this spot. And we know L. So how do we do about it? Well, let's find this angle. Let's call it theta. Let's call it alpha. Can we work out alpha? Well, we can, certainly. Alpha is, in fact, equal to theta 1. Because if you look at this angle, so this angle, so this is theta 1. This is theta 1. This is, we don't know, this is alpha. Alpha. This is 90 degrees. This is theta 1. So this must be 90 minus theta 1. So if this is 90 minus theta 1, this is theta 1. Oh, no, sorry. That's theta 1. That's theta 1. And this is theta 1. Sorry, that's theta 1. So this must be alpha. So alpha is 90 minus theta 1. Sorry, 90 minus theta 1. And we can find this distance. So this is alpha. But if this is alpha, that means that this is theta 1 and this is theta 1. Okay, so we don't really need alpha here. We can use theta 1. And let's call this distance x1 and we'll call this distance x2. So sine, now we're going to use a lot of trigonometry here. So for the top triangle, for this triangle, we have cos theta 1 is r over x1. And for this one, sine theta 1 is x2 over, tan. We can use tan. Tan theta 1 is x2 over r. Okay. And, well, actually, we need to find x1 first. Because what if, okay, let's find x1. x1 is r divided by cos theta 1, which is 2 root 2, which is approximately 2.82. Okay, 2.82, so it's actually, so yeah, so x2 must be 2 centimeters. And now we can work out r and tan 45. So tan 45, that's x2 over r. And r must equal to x2, which is 2 centimeters. And therefore, we found it. It's 2 centimeters. The radius of the bright spot is 2 centimeters. Okay. So, how these questions work is first you need to work out what's going on from the point of view of physics, and then you just need to do some constructions, some trigonometry and some geometry to find what you need. On a scale of 0 to 10, do you think you will be able to do this exact question if I gave it to you right now? Okay. All right, I got some responses. Okay, it is a tough question. I mean, honestly, like it is quite an advanced question. Well, try to do it. Try to do it by yourself. I've got another quite a tough question. So I might not do Fermat's principle. We'll see. We'll see how it goes. Problem 6. A laser hits a glass prism at right angles. At a right angle. The prism has an angle alpha 10 degrees. Refractive index is 41. How many bright spots will be seen on the screen? That's a very weird question to ask. Why would there be spots on the screen? Well, let's see what's going on. Let's try to imagine. So light enters the glass prism. So it's sort of like this. One side is rough. So you can immediately see that the light doesn't enter because the angle is so large. I can't change that angle, unfortunately. But yeah. So how it goes, that light let me make another picture. And I think it's one of the questions on the assignment. At least it's very similar to one of the questions on the assignment. Okay. So light comes in. It doesn't refract at the boundary because it's 90 degrees. Now it reflects. It reflects here, but it also refracts. So some of the light goes through. And you see a bright spot on the screen. Now some of the light reflects at a different angle. Now it reflects again, and some of it is refracted out of the glass, and you see another bright spot. And some of it is reflected again, and reflected again, and some of it is refracted. So you see another bright spot. So this is how it goes. Let me try to change this angle a little bit, because that seems excessive. Okay, so with a shallow angle, it goes like this. Some of the light goes through, and it is refracted, reflected, reflected again, refracted, reflected, refracted, reflected. And as you can see, this angle gets bigger and bigger and bigger, and so at some point you just have internal reflection, and you have light bouncing back and forth and not reaching. So at some point you have total internal reflection. Total internal reflection. All right, so for total internal reflection, we first need to work out the critical angle. So the critical angle is 1 over n, inverse sine of 1 over n, which is approximately 45 degrees. We've already established that. So 45 degrees is the critical angle. Okay. So if light falls for the first reflection, when light falls onto the boundary, the angle of incidence, this is the normal line, this is the angle of incidence, so that will be, well, because this is 10 alpha, so this is 90 minus alpha, so that's alpha. So the angle of incidence, the first reflection, angle of incidence incidence equals alpha. Now it reflects, and it reflects with the same angle, so that's alpha. It reflects here again, so this is 12, that's 2 alpha. So it reflects at 2 alpha, and if it's 2 alpha, that it hits the boundary, it now hits the boundary at an angle of, what's the angle? So this is horizontal. So this is 2 alpha. This is horizontal. So this is 2 alpha. So this is 2 alpha. This is 2 alpha. Now, if this was horizontal, that would be 2 alpha. But it's actually 3 alpha now. 3 alpha. And then it's 3 alpha. So that's 6 alpha. Plus another alpha, 7 alpha. Does that make sense? So first reflection, I go is in second reflection. This is once. This is the second one. Second reflection. So the angle of incidence is 3 alpha. And I think it adds 2 alpha for each consecutive one. It's either 1 alpha or 2 alpha. Let me just double check. So goes straight through, bounces. Now, if this is alpha, it bounces off. This is alpha. And if this was horizontal, that would be alpha. But because it's tilted, oh, it's 2 alpha. Sorry. First reflection and second reflection is 2 alpha. So every time 2 alpha, third is 3 alpha, etc. But alpha is 10 degrees. 10 degrees. And the criteria is if the angle of incidence is less than the critical, you have refraction. So you have a bright spot. If the angle of incidence is greater than the critical, then you have no reflection. You have no refraction. You have total internal reflection. So 20 is fine. 30 degrees, fine. 4 alpha, that's 40 degrees, that's fine. And then 5 alpha, which is 50 degrees, no, that's greater than the critical, so no refraction. So refraction, 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 no refraction. So you have 4 bright spots. So the answer is 4 bright spots. Right. So the difficulty in this task is to draw good angles effectively. And no, I think I've made him. I think no. No. Apologies. Okay. Once again. So you have two lines. So you have a ray of light going through. Now it is reflected. It is reflected. Now if we zoom, why can't we zoom in? If we zoom in, we will see that if this is the normal line, then this is alpha. This is alpha. So that means that this is 2 alpha. If this is 2 alpha and this is 2 alpha, then this is 3 alpha. 3 alpha and 3 alpha. Now, that's 3 alpha and another alpha. So go back. So that's 4 alpha. 4 alpha. 4 alpha here. 4 alpha. Yes, that was right the first time. So that's actually 5 alpha. So first reflection is alpha. Second is 3 alpha. So in the first instance, you have refraction. In the second instance, you still have refraction. In the third instance, you don't have refraction. You only have reflection. So here, at this point, you have reflection plus refraction. Because the angle of incidence is alpha, which is 10 degrees, which is less than the critical angle, less than 45. Here, at this point, you still have reflection plus refraction, reflection plus refraction, because the angle of incidence is 3 alpha, which is 30 degrees, which is less than 45. Now for the third, you only have reflection only, because the angle of incidence is 5 alpha, which is 50 degrees, which is greater than 45 degrees. So that's how it works. Apologies for making a mess. Okay, so second reflection angle of incidence 3. So here, no. 30 degrees. 5 alpha, which is 50 degrees. So 2 bright spots. 2 bright spots. Does that make sense? Do you think you understand this question? Final thing that I wanted to talk about, but maybe I should have chosen easier problems today, but I have done easier problems, so do find my year 12 webinars from last year's. They will be, some of them will be easier. So please do. So Fermat's principle, reflection and reflection. So the Fermat's principle says that light chooses the shortest possible path. So imagine that this is a mirror. And light needs to travel from A to B. And imagine that, I don't know, there's some obstacle here, so it can't pass directly through. So it needs to bounce off the mirror. And there are different possible scenarios. It can go like this. It can go like this. Or it can go it goes like this. And Fermat's principle says that light chooses the quickest path. Light chooses the quickest path. And it turns out that if you were to actually find the quickest path would satisfy the law of reflection. The quickest path would be the path where theta 1 is equal to theta 2. This happens if theta 1 is equal to theta 2. And this is proof in the webinar. In assignment. So what we do is we take this to be h, and we call this h small, and then we have this distance L and this distance x, and we work out the time it takes to travel from A to M and from M to B. So time from A to M is equal to h well, it's distance divided by speed. So that's square root of h squared plus x squared divided by speed of light, c, and time from M to B. That's the distance mb divided by the speed of light. So that's mb divided by speed of light, which is c. mb is square root of h squared plus 2l minus x squared. Well, we can safely assume that this is the same h. Let's not bother too much about it. To have extra letters divided by c. And then the total time is square root of h squared plus x squared divided by c. And t plus square root of h squared plus l minus x squared divided by c. And then if you differentiate that, if you do dt over dx, you find the derivative of the time with respect to x, and you get something. Well, let's do this. It's going to be 2x multiplied by 1 over 2 root h squared plus x squared, c, of course, plus 2x minus 2 L over 2 times square root of h squared plus L minus x squared c, and that must equal to 0. I can cancel the c's, I can cancel the 2's. I get 1 over square root of h squared plus x squared plus x minus L. Oh, sorry, that's x minus L square root of h squared plus L minus x squared equals 0. Okay, this is going to be interesting. So x over h squared, x, but that's theta 1. So that's theta 1. So you got x over this, x over am. But that's sine theta. That's sine theta 1 plus x minus L over h squared plus, that's this distance. That's L minus x. So that's minus sine theta 2 equals 0. Therefore, sine theta 1 equals sine theta 2. And that's equal, theta 1 equals to theta 2. So I just proved it. Okay. And the Fermat's principle for refraction works in a very similar way. So let's say you have water and air, and you're traveling from A to B. Light is traveling from A to B, and it chooses this path. And this is theta 1, and this is theta 2. Okay, and then it turns out that the quickest it can get from A to B is traveling in such a way, path is quickest if sine theta 1 and 1 sine theta 1 is equal to n2 sine theta 2. And you prove it in a very similar fashion. Unfortunately, I have to go. The link to the webinar is here. Miro link. Okay, and yeah. Okay, so please do have a look at my old Year 12 webinars. You might pick up some interesting stuff. I really hope it was useful for you today, and I'll see you in 2 weeks' time. So I'll see you on the 4th of February. So we're going to talk about geometry. Okay, see you everyone. Bye.